Now let's take a look at this figure 14-7. And this figure deals with high efficiency motors. You know, they come in a NEMA B high efficiency or a Design E type motor from the European market. But notice how they're designed. To the left, has a high efficiency fan blade that causes the motor to run a lot cooler. It's sandwiched steel to reduce the eddy currents big time. Better steel reduces the magnetic losses. And windings equipped with more copper gives the motor more power, and it reduces the I square R losses. The rotor bars and rings are bigger, reduces motor losses. And of course you see the pigtail here going to the controller and the disconnecting mains. The only thing about these motors is they have a very high inrush current because you're building with the steel and everything better, and it reduces resistance and impedance of the motor, so it really draws a lot more inrush current, just like a transformer. You know, if you had a transformer that put out 1,000 amps and you had a 2% impedance on the transformer, well, 2% into say 1,000 amps, 50,000 amps. And say that you said, no, I'm going to raise that impedance to 4%, then 4% into 1,000, it'd only be 25,000 amps of short circuit current. So same thing with a motor. If you lower the impedance and everything of the motor, it's going to have more inrush current. And that's why the National Electrical Code in 430.52C3 and the exception would allow you to go up to as high as 1,700% to allow high efficiency motors to start that could draw up as high as 15 times. Now, as a rule of thumb, I've been told that if you buy a high efficiency motor that really doesn't pay you back as fast using it and purchasing it, it starts at about 8.5 times the nameplate current. If you bought the next, it'd be 10, then 12, and 15. So that's why the code would go up to 1,700% to let this motor start and drive its load. But it's a high efficiency motor that doesn't pull as much current-wise that would cause the bill to be higher for running it. So it's just a high efficiency type motor that many of our manufacturers manufacture for if someone wants to purchase it and use it. But you got to be careful, fellas. If you're out there and somebody wants to purchase this, make sure the existing system will allow this high efficiency motor to start without you having to buy a solid state starter or some reduced starting means, which you can find all that in the Stallcup's generator, transformer, motor, and compressor book, how you'd go about this. So remember, a circuit breaker, about 600 volts or less, basically will pull 3 times its rating. So if you had a 100 amp circuit breaker, 300 amps. If you had a fuse now, they'll pull about 5 times their rating. So that'd be 5 times 100, 500 amps. So you can see it's very important. What is your existing system? If it's an instantaneous trip circuit breaker, how high will the instantaneous trip be allowed to set? And can you set it above the inrush starting current of this high efficiency motor, which would be very high? Now you can go through the book, Stallcup's Generator, Transformer, Motor book. All these items are discussed in detail so that you don't foul up there. But basically, this figure 14-7 is illustrating a high-efficiency motor and how they are designed and manufactured, either using say a NEMA B high-efficiency motor or a IEC Design E motor.